Okay, so good evening, guys. My name is Guillermo Cuerva, and today I'll be presenting my advances on my thesis, Turbulent Transport Characterization in Hall Effect Thrusters, supervised by Eduardo Aedo and Miguel Pérez Encinar. So we have talked about in the last couple presentations about Hall thrusters, and it's basically it's used for in-space operation due to its high specific impulse, and it's a very mature and well-established technology. However, there's two main open problems, which are the anomalous electron transport and plasma wall interaction. They have talked about in the last couple presentations about anomalous electron transport, but what is it? Okay, so what happens is that in a plasma, in this type of plasmas, you're gonna have a magnetic field that is gonna confine the electrons, but not the ions. So basically, the electrons are gonna gyrate or do orbits around the magnetic field lines, and they move also parallel to it. Since you also have an electric field that will accelerate the ions, what will happen is that the electrons will experience a drift in the azimuthal direction due to the cross product between the electric field and the magnetic field. But they also experimentally, you see axial drift of electrons that go from the cathode to the anode, that if you estimate it through collisions is way larger than what is supposed to be. So basically, this transport should be enhanced by either plasma wall interactions or azimuthal oscillations and plasma turbulence. And in this thesis, we focus on the later one. So what are the main goals of this thesis? Basically, the numerical study of the main kinetic instabilities in Hall thrusters and try to contribute in 3 areas, more or less. So what are the main instability modes triggering plasma turbulence in Hall thrusters? Develop reliable and computationally feasible numerical models of the plasma discharge, as well as how we can extrapolate those findings into a simplified turbulence model. Basically, we extend the work previously established by Alberto and Enrique. So how we do the numerical study? Basically, we use a particle in cell approach, which basically, in plain words, is basically I like to move particles around. So the idea is that instead of solving the distribution function of electrons and ions, I'll simulate macroparticles in a grid domain and move them with an electrical force and move them with the electric force that they experience as well as the magnetic force. And the idea is that in this type of peak codes, my thesis was more or less separated into the improvement of the Picasso code, which is the code developed by Enrique and Alberto, and the GPU-based kinetic simulations that we just started to develop. Last year, I talked about a lot on the improvement of Picasso, so I decided this year to not talk about it, but if you have questions, then I'll be happy to answer them. So we'll just focus on the GPU simulations and why they are important. So basically, this type of CPU, the Picasso code has some limitations. Basically, in this type of plasmas, you're required to solve the electron dynamics and the bit length and the timescales, as well as they have to be run long enough and to capture quasi-steady state. So since this is computationally very expensive, usually people apply artificial scaling on the vacuum permittivity. So we use GPUs because allow us for a massive parallelization, as well as not having any artificial scaling on the vacuum permittivity, high resolution, and good statistical accuracy, since we are allowed to put more particles in our grid, basically. So coming back to the anomalous electron transport, so the idea was to analyze a simplified scenario. We know that this type of transport is highly dominant in the acceleration region of the Hall thruster and is driven by azimuthal instabilities. So the acceleration region is this box here. So basically, you already have all your ions generated. They are going to be axially accelerated by the electric field, and you're going to have a magnetic field that is confining the electrons. So the idea is to do a simplified configuration and try to analyze the impact of these instabilities without the added complexity of magnetic field gradients, collisions, etc. And try to do some parametric studies to study if we can have an scaling law or a dimension analysis. So basically, this is the domain that we are simulating the GPU, which is just a domain of a rectangular domain, basically, with a fixed potential drop in the Hall acceleration region, with a constant magnetic field, and you inject a cloud of plasma at the entrance, so the E, and you also inject a cloud of electrons coming from the anode at the exit, which is the C, okay? So then we can go on the transient response of this type of simulations. If you have questions of the inputs, I can answer them on on the question section. So basically, we're going to look at the anomalous current, so basically the axial current evolution over time, and how the azimuthal instabilities develop on the azimuthal electric field, basically. So what you see here is that you start with an onset of those instabilities that appear, and then after 4 microseconds, more or less, you have consistent coherent structures from 5 to 15 millimeters of our domain that are maintaining over time, and it will generate a constant axial electron current on our domain. I could show you a lot of plots of it, but the main takes will be probably on the electron momentum balance and the energy balances of electrons. So basically, first, if we look at the electron momentum balance, we see you have the magnetic force is fully balanced by an anomalous force, which is a combination of the instability one, which is the electric force, as well as a finite Larmor radius effects, which are the pressure and inertia terms. You have two separate regions in which, on the right, from 7.5 millimeters onwards, the electric force dominates, which is basically the region where the coherent structures appear, and then on the other side, you have the finite Larmor radius effects. Then you can also look at the energy balance, and the main take of this is that you have a contribution on the work of the azimuthal electric field, which is the yellow line over there. So basically, you see that you have a region in which this is taking energy from the electrons, which is the beginning, and then it's giving energy to the electrons from 5 millimeters onwards. So basically, this is something that in the literature is not seen, and is something pretty new, to be honest. Then another thing that we can analyze, okay, I give you a simulation, but then what we can do is vary different parameters. So basically, similar to what Tatiana did, is that you can modify the potential discharge, the potential drop, the magnetic field, and the electron density. So when you look at the potential drop, what you see is that a higher potential drop will have a higher E cross B drift for electrons, but what you see is that there's a point in time in which there's point in the potential drop in which the potential is, the anomalous electron current does not increase anymore. It starts to decrease up to from 250 onwards, which is quite interesting because it was something that I did not expect. On the magnetic field, well, you see something that for higher magnetic fields, your electrons are highly confined, so then your anomalous electron current starts to decrease very drastically, which is something surprising because on a Hall thruster, you have higher magnetic fields than the one that I'm simulating here, but you also have magnetic field gradients, so maybe that can play a role. And finally, that your anomalous electron current is proportional to the increase in electron density, so basically up to 4 10 to the 7 meters cubes of electrons, you see that the electron anomalous current starts to increase. Finally, I had a lot of troubles during this year on something that is called the numerical thermalization. So basically something that happens in the fact that you are considering macroparticles, which are seeing a finite number of macroparticles, so it means that it gives you a noise on the simulations that you have. And depending on the parameters that you select, this type of noise can provide a numerical anomalous current, and therefore have an overestimation on all the current that are actually seen. So therefore, we need to be careful when to trust the simulations. For example, the ones that I showed you in the last year, you see that even up to 12,800 particles per cell, which is something that a CPU code can never do, even the density keeps varying, it keeps increasing. But with this new scenario, what you see is that between 400 and 800 particles per cell initially, the density is the same, and the anomalous current also is the same, okay? So, summary and current photon work. On the GPU-based, we did 2D peak simulations of the acceleration region, and we started to look into how these instabilities affect your plasma, and as well as trying to understand what happens if we change some parameters of it. And also, something that I did not say is that this parametric study can be done because of the GPU. This type of simulations on the GPU take around 17 hours, whereas in a CPU-based code, take considerably more time. And then also, you need to be careful on the numerical thermalization and try to do convergence studies to analyze what happens if you change the number of particles per cell and try to see what's going on, basically. And I didn't talk about the axial peak simulation with Hall effects, but if you have questions, I'll try to answer them. And these are the conferences that I attended and the manuscripts that we are trying to prepare, or at least analyzing the results in order to get publications on. So thank you very much. I'll try to answer questions.